described vertically. I'm going to then have my eigenvalues just like multiplied by the identity down here. So we've got the eigenvalues down here and zeros everywhere else. And then I've got P prime, which is once again the same thing here, the eigenvectors, but now expressed as rows, right? And that's how we can actually decompose any matrix in that manner. Right? So this is called the spectral decomposition of your matrix. Right? Basically, it's decomposing your original matrix or your model into a form of eigenvectors and its eigenvalues. When you multiply them together, you can recreate your original matrix. Right? But it's got the new basis function. Right, so it's the canonical form is when we have these lambdas arranged from biggest to smallest down here, and then we've got zeros along the diagonal. Right, so the spectral decomposition of this matrix here, 1, 1, 9, 4. Okay, this is not a variance-covariance matrix, so we can get some funky eigenvalues potentially from this. Right, we end up with a negative eigenvalue, right? That wouldn't make any sense to have a negative eigenvalue in a variance-covariance matrix, right? It would mean that you've got a negative variance. But because this is not symmetric, it doesn't really matter. It's not a variance-covariance matrix. Right, so we know in this instance, we know what lambda is. It's 5 and 7. No, sorry, negative 5 and 7. We know what the two eigenvectors are. Right? Oops. Oh, did I remove that? Oh, okay, I did. So, oops, doesn't matter. I thought I gave you an example of I'm actually doing the spectral decomposition of this, but I might have thought I'd leave it as an exercise for you guys. Probably not for a Friday afternoon. Okay, so this is what we get, right? We've gone through, basically we know all the steps now, from the raw data matrix to the eigenvalue deconstruction of it, all the way down to its spectral decomposition, to our principal components, our U matrix, right? So if we want to work that out, what is our new component scores? Well, I've told you the math behind that, right? Using E prime E, right? Here's P, right? That's a vector of a matrix containing all of your eigenvectors, right? So U is equal to your original data values times your P matrix, right? And that gives you your actual scores and your new PC rotated PC axis. Okay, so that means your scores are simply a linear combination of the original variables, right? So what have we got? What have we got here? We've got, hey look, let's say I is equal to 2, so it's a second number for variable 1. So this is going to be equal to a particular value for variable 1. This is the second number, an eigenvector 1, given here. So that should say I, shouldn't it? That should say E1I, if I've given an I here. Oh no, this is for the first value, number. So that's fine. And then I do that, calculate that for all of the variables. That should also be subscripted, sorry. As should that. What error is it that I now see? And you can actually then work out your, basically, this gives you your new coordinate system, in short. Okay. So these are the eigenvectors for your precipitation. We've seen that already. We know what that is. We've already done this, so that's fine. Okay, so let's summarize PCA. Is that what I'm trying to show here? Nope. Sorry. So PCA, right? New axes. Linear combinations of the original variables. The first axis explains the most variation through the cloud of your data. You know that. Each successive axis is at right angles to that, to the first one, and then to the later ones as well. And they are explaining successively less and less variation in the data cloud. So the first two are the most that we can explain with the two axes. So typically all you're going to do is plot those first two PC axes, right? Which means find your axes, convert your data points into the PC scores, right? And then, which is exactly what we did using SAS, right? You find your new, basically your rotation that does that, and then consider how much of the variation is explained by those first two PC axes, right? The more the variation explained, the better the representation of the full dimensional data cloud you've got. So in theory, you've got as many axes as you do original variables, right? And if you use all of the PC axes, right, all you've done, basically, you've got a data cloud and you've just drawn a new set of axes through it. So of course, you're going to describe all of the variation, just like you had before. Right? But the new space is sort of is being centered according to the center of the data cloud. It's just a rotation of the data cloud, then, so that all of your axes are orthogonal to one another. It preserves Euclidean distance, which is not something you need to worry about, except that biologists use non-Euclidean distances typically. When we're doing our analyses of our data, we like things like Bray-Curtis measures and stuff like that. But for most of you, since there's no real biologists here, I'm not going to go on about that. Usually I have to a bit. This is something that we talked about before. The sign of each eigenvector and each PC axis is arbitrary, right? So we can reflect it. And this is what we found with those bubble plots, right? Remember I had some bubbles on the right-hand side, and you guys, when you calculated them, they were all on the left-hand side, right? But the interpretation was the same, because it doesn't matter as long as those vectors are still pointing and are also reflected as well. So the sign of each eigenvector is in fact arbitrary, right? It's just the general direction that's important. So this is important, and that is that the PCA is usually done on the correlation matrix, not on the variance-covariance matrix, right? And that's because you don't want those variables that have, just naturally got an enormous amount of variation in it to dominate the analysis. Typically you want all of the variables to have the same sort of input and the same sort of weight when you do your PCA, right? So that's why you standardize things, or you just use your correlation matrix, right? The correlation matrix, remember, is just the standardized covariance matrix. So apart from that, they're the same thing, right? So this is in fact the same thing. If I take the raw data and then I standardize it, and then do a covariance matrix of my standardized data, I get a PCA, right? It's exactly the same thing as doing the raw data, calculating the correlation matrix straight from the raw data, and do my PCA, right? It's identical to one another. Right? So there's no difference in these things. Typically, this is what people do, because correlation matrices, as you can see, right? If you look at the covariance matrix of something, well, what does it mean? But the correlation matrix, since we've got this lower bound of -1 and an upper bound of 1, and we know that a 0 means something, right? It is put on a scale that we can interpret. So people typically use this path, right? They go down the correlation matrix, and they calculate the PCA from that. So if you did so this is saying, hey, look, if we do a PCA on the correlation matrix R, and this is a PCA on the variance-covariance matrix, right? If you do it directly on the variance-covariance matrix, what happens? Well, the sum of the eigenvalues is going to be equal to the sum of the variances, right? Because remember, in the variance-covariance matrix, the trace is not equal, those values aren't equal to 1, right? Whereas in a correlation matrix, all of those values along the diagonal, all the variances are being standardized to be 1, right? So the sum of the eigenvalues is simply equal to however many variables you've got, right? So if you haven't standardized things, then the distances amongst the objects, amongst your data points, will depend on your measurement units. Right? You can be dominated by those variables that have a great deal of variation. Here, you've got distances amongst your data points that are independent of the measurement units, right, because you've standardized things. And if you've standardized things, then all the variables are contributing equally, basically, depending on the variation. They're all just expressed in standard deviations of units. Well, if you haven't standardized things, then those variables that are hugely variable will contribute more to the PC. Right? They'll be more heavily weighted just because they have more variation in them. Right? So if you haven't standardized, then the eigenvector weights will depend on the scales of the variables, so you can't directly compare things. So the short answer is, in nearly all situations, people standardize their data. Right? They standardize the data, which is the same thing as doing the eigenvalue deconstruction on a correlation matrix. Right? That's the take-home message. So scale matters. So usually, your variables are not dimensionally homogeneous. What do I mean by that? I mean that usually I'm measuring something and it might be in grams, and then I'm measuring something and it might be in meters or in tons, so they're not all on the same scale. And if that's the case, it's important that I standardize all of those variables, right? If they are dimensionally homogeneous, right? If they're all measurements, that range from 1 to 10 or 1 to 16 or something like that, then it would make sense to do a PCA on the covariance matrix. Okay? Maybe those variables that happen to be more variable, that actually means something now. The actual variation of a variable is important. It shouldn't have been just standardized to have a variance of 1. So I don't want to throw away that information. But this doesn't happen very often. Well, not for me as a biologist. As a practitioner, if you're dealing with surveys, maybe it happens quite a lot, actually. Because maybe you're measuring things that always have a value. All your variables have a value between 1 and 10 or something like that. Right? So anyway, that's something to keep in mind. Right? To me, I always think, well, if I do a PCA, I need to do it on the correlation matrix. Because all of my values, my counts of my animals that I measure, they're all different scales. Right? It doesn't make sense to have them on different scales. Okay, so we use PCA. This was brought up, right, when we have quantitative data. If we have qualitative data, we don't have any idea what covariances mean, particularly, right? We've got group membership. Those vary with respect to a mean. Yeah, it's not obvious. It works well if your data are approximately normally distributed. Right? In particular, it works well if you don't have any outliers. As soon as you have an outlier, right, it's probably going to draw your PC1 axis towards it, right? So the PC1 is usually going to point towards that, even if it's not particularly meaningful in the grand scheme of things. So it is a bit problematic if you've got very skewed data to try and do this sort of analysis. That's why biologists, when we're dealing with our count data, we almost never use PCA. We'll use something that I'll teach you tomorrow called NDS. And it works well if the number of variables is less than the number of observations that you've got. Right? If the number of observations is a lot less than the number of variables, well, SAS can still come up with a solution, but it's not your covariance matrix or your correlation matrix is not very stable. Right? So it's likely not to be a very good solution. So if you've got highly over-dispersed data, if you've got lots of zeros and some big values, you've got big skewness in the data, this is basically the same point as this one here, then it's a problem to do a PCA. It can give misleading results due to those outliers. Okay, so for a PCA to work, right, it's like magic, right? You start off with 15 dimensions, you chop it down to 2. It won't work if there's no correlation amongst your variables. You can't do it, right? If there's no correlation amongst your variables, mind you, then you might as well look at each one independently, right? So that's problem solved. You might as well do just 15 univariate analyses. The whole point of doing a multivariate analysis is if there is structure in the data, right? If there's structure in the data that is not spotted just by looking at the points individually, the variables individually, right? Then that's when you use a multivariate analysis. And that's when PCA will be useful, potentially. So it works really well if there is quite high correlation amongst your variables. Okay, so how many PCA axes should I plot? This is an important thing. Well, we've learned about scree plots. A scree plot, remember, describes the variation explained by each additional axis, and that could either be by plotting the eigenvalue relative to the number of axes, or the amount of variation explained. And remember, and what we're doing is we're looking for an elbow. So just to reiterate, a scree plot is PC1, PC2, PC3, PC4, right? If these guys have quite high values, and then PC4 has a low value, right, like this, then you would probably say, hey, look, the number of axes that I would use is 3, because after that, the fourth one and everything else after it doesn't really contribute a great deal relative to these things. So you look for the elbow in the plot. As a general rule of thumb, and this is a very general rule, a good plot will capture around, or at least 70% of the variation in the data, right? So there's some rules of thumbs that we use. Hey, look, if you're explaining 70% of the total variation in my high dimensional data cloud, then that's probably a pretty good representation. I'm not throwing away too much of the data, right? Some of the plots that we were looking at, right, there was only explaining about 50% of the variation. What was the movie data? That was about 50%, right? Or 40%? Have I still got it? It was 31 and 13, so about 44%, right? So this would be considered, you know, it's not a particularly good representation. We're throwing away a lot of information in the movie data, right? And it was because it was a 46-dimensional space that was compacted down to 2, right? So it's not particularly surprising. Sometimes if you get really strong trends, actually, and people really feel very strongly in the same way, it actually captures it really well in 2 dimensions. But I tried to mix up the movies this year to try and get a good range of everything. And I think as a consequence, it sort of homogenized everything. I think the one thing we can agree on is that we all hate The Notebook in Love Actually. You know, apart from Cyrus and Alice and Joanne. Okay, so where was I? Scree plots, that's right. Right, so we didn't actually produce a great plot, but it wasn't a, you know, as I talked to you guys and asked you questions, well, does this represent you? Most of you would say, yeah, actually, it kind of characterized your thoughts on those movies pretty well. And I was only explaining about 50% of the variation in the data, right? So a good plot will capture around 70% of the variation, right? We know about the high correlations, so no need to repeat that. So it's not so obvious for the pollution data, right? If we were to look at the eigenvalues in the scree plot, it looks like this. There's no obvious elbow. So this is the same sort of information that's being explained, right? The variation explained. And this is kind of frustrating because where do you draw the line? How many axes do I need, right? Some people like to use a rule of thumb where they'll grab everything above 70 or 80%. Everything, the number of axes required to get to that. Some will say, well, I'll grab everything where all my eigenvalues are greater than 1, right? That would say, okay, 5 axes. There is no solid answer for it. But remember, if I was to create a random ball of noise, right, where there is no real structure to that, my scree plot would still be decreasing like this a little bit. Right? So some people try and generate data and have a look at the scree